everybody. Today I'm going to be talking to y'all about the sun, so particularly where the energy that powers the sun comes from, and a little bit about the solar interior. So let's start off with some 19th century theories. So one of the theories for where does the sun get its energy was through gravitational energy. So one theory was that gravitational energy would pull in, converting that would convert into heat and power the sun. The problem with this was that estimates would make the sun only about 100 million years old for gravitational energy to be powering the sun. And at the time, back in the 19th century, that seemed like enough time. We thought that the Earth wasn't older than that. But it turns out that the Earth and the sun are much older than that. So gravitational energy is not the main way that the sun gets its energy. Another thought was that there was something chemical happening. So there was something burning or oxidizing like wood or coal, or just something was burning. The problem with this theory was that the sun would only last a few thousand years at that size and how much energy was being put out by the sun. So that theory was also thrown out. And then there was another theory that the sun got its energy through collisions with meteorites. So lots and lots of meteorites were colliding with the sun, powering it. The main problem with this was that for that many thousands of meteorites to cause that much energy to be created, there would be a really big increase in mass of the sun, and that would change orbital periods for planets. And so that was also thrown out as a theory. Not until the 20th century was the actual source of energy for the sun discovered and explained. And this was through the idea of mass energy equivalence. Einstein came up with his famous equation, E equals mc squared, which relates energy to mass, mass times the speed of light squared. And that was huge. So a particle can be converted into energy and vice versa, which allows for the sun to essentially generate power. So the sun converts mass into energy. It does this by converting 4 million tons of matter into energy per second, which is a lot, but the sun is also extremely massive, so it's not, running out of mass. It does this through a fusion process. So here's our picture of an atom. We've got a neutron and a proton in the nucleus and an electron orbiting that nucleus. Again, protons, electrons, and neutrons. Protons are positively charged and electrons are negative. And there are antiparticles made of antimatter for these particles. When antiparticles come into contact with not antimatter particles, they annihilate each other and emit energy. So here's a little diagram. Let's say this is an electron and its antiparticle, a positron. If they come into contact, they annihilate each other. So they cease to exist, and they're converted into energy in the form of, let's say, a gamma ray. And the reason that antiparticles are created is because of the conservation of charge. So if through some process an electron is created, that's a negative charge, there needs to be a positive charge to balance that out and follow with the conservation of charge. So if the fusion process, when particles come together to form a nucleus, binding energy is released. And that's because, let's say we have two protons that come together. They each have some mass. When they bind together in a fusion process, that new nucleus actually has less mass than the individual particles themselves. So that change in mass is converted to energy, which is called binding energy. And binding energy is released up until iron. So elements that are lighter than iron can bind together in a fusion process, which releases binding energy. Elements that are heavier than that, those are the elements that if we break them apart, they release energy. So those are those elements that we can break apart with fission. Um, so that's how we can use uranium and plutonium in nuclear reactors with a fission process to break them apart and generate electricity at nuclear power plants. So the fusion process in the core of the sun has three main steps. Step one, we have two protons drawn here as H with a 1 to represent hydrogen, a hydrogen atom with just one proton. I guess nucleus, not atom. Two protons come together, and when they collide, they create a hydrogen isotope called deuterium that has one proton and one neutron. In the process, a positron is also created because here I've got two positive charges coming in. I've got one positive charge in this new nucleus, and so there's another positive particle that's created. There's also a neutrino that's emitted. So originally the neutrino was kind of like a desperate solution because in this process there was unaccounted for energy, and who was it? Pauli just named the neutrino. He had no like physical proof that this neutrino existed, but he just named. He's like, there has to be another particle. He thought it was massless, kind of like a photon. Actually, in 1998, they finally did measure the mass of a neutrino. It's tiny. It's like 1/500,000th of an electron. But it was originally named just to account for some extra energy. But it turns out that a neutrino does exist. It's a very tiny particle that barely interacts with matter. So that's step one. Step two, in this process, we have the deuterium particle here collides with another proton to create helium-3. So we've got two protons in the nucleus now and one neutron. So it's an isotope of helium. And a gamma ray is emitted in this process. And then the third step in this cycle here is two helium-3 nuclei coming together and creating a stable helium nucleus, which is two protons and two neutrons. And then there are two protons at the end of this cycle that are a product and can then start over this cycle. So this is called the proton-proton chain. Here are those same steps written out in more of a chemical or a chemistry way. So again, mass is being converted into energy. To imagine how much energy is being generated in this process. So if you had 1 kilogram of hydrogen to start out with, this process would lose only about 0.0071 kilograms of mass in this whole process, but that amount of mass is equal to 6.4 times 10 to the 14th joules, which is an incredible amount of energy, and that is how this process is able to power the sun, which is obviously generating lots and lots of energy. Okay, so again, a neutrino is super, super small particle, and it weakly interacts with matter. And a little bit more about the positron here. So a positron will annihilate electrons because a positron is the antiparticle of an electron, and it releases gamma rays. That's happening in the center of the sun. So that gamma ray is then absorbed by other particles and then re-emitted at lower energy. So by the time that these photons reach the surface of the sun, it can take 100,000 to 1,000,000 years just because it is so dense in the center of the sun that those gamma rays or X-rays just keep running into things. So they keep being absorbed and then re-emitted. But by the time that they reach the surface of the sun, not all of them, but most of them are in the visible range because that is the most common frequency that our sun emits. Obviously, there's going to be some in the UV range or in the lower range, but the photons do take so long to reach the surface of the sun that they are emitted at a lower frequency. The solar interior, sorry about my dogs. The solar interior is plasma. well, the whole sun is plasma, which is hot ionized gas. The sun is at equilibrium, so that means that the gravity pulling inwards balances with the pressure of the hot gas pushing outwards. So that is why the sun is able to stay at equilibrium and stay stable. So here's a picture from our book. So this is in the blue range. This is in the center of the sun, and then going outwards. So where nuclear fusion is happening, the temperature is about 15 million Kelvin. It takes 12 million Kelvin for this fusion process to occur, so that's plenty hot enough in the center of the sun. And then it does decrease as you go outwards. And then the density also is very, very dense in the middle of the sun, and then decreases towards the outside surface. And so here's an image of the heat transfer within the sun. So inside the center of the sun, that's mainly heat transfer through radiation. So in the center, we have fusion processes going on. There's a lot of gamma particles that are radiating, and eventually, they're losing some energy as they radiate out. This outer layer of the sun is a convection zone. So think about convection in your oven. There's a rising and falling of rising hot and then falling cool. And so that's kind of how heat transfer happens in the sun. Thanks a lot, and see y'all next week for my last CD.